Welcome to In Depth with Academia. I'm Richard Price, CEO of academia.edu, and today, wow, do we have a fascinating and thought-provoking paper to discuss. We're diving into dark matter as the difference of inertial and gravitational mass. Yeah, you heard that right. The title might sound a bit dense, but trust me, this idea could change how you look at the universe. First, as always, I'm here to present this work neutrally. I'm not endorsing or debating, just sharing the author's perspective so you can ponder it yourself. Academic research is always evolving. Nothing is set in stone, right? This is our chance to explore and reflect. So let's start with the basics. The author is David Lush. His paper tackles one of the biggest mysteries in modern physics. What is dark matter? For decades, astronomers have realized galaxies rotate way too fast. If we only count the stars and gas we can actually see, there's got to be more mass out there, something invisible, hence dark matter. But here's the problem. After years of searching, physicists haven't actually detected any candidate dark matter particles. No definitive sign of these mysterious things. So what if we're looking at this all wrong? What if we don't need exotic new particles? David Lush's paper suggests an alternative. The core question, what if the gravitational mass of ordinary matter is actually bigger than its so-called inertial mass? And crucially, what if this difference is enough to account for all those galactic oddities? That's a wild idea, but let's break down what it means. Okay, pause for a second. Let's digress. You know, this reminds me of when I first tried to assemble my own IKEA bookshelf and realized halfway through that maybe I misunderstood the instructions. Sometimes maybe the answer isn't to look for a missing piece under the sofa, but to look at the instructions from a new angle. Anyway, back to dark matter. So the paper draws on two not so mainstream ideas from theoretical physics. First, there's a proposed revision of special relativity by Osiak. It says basically that Einstein's equations for energy might not capture the whole picture. And the second idea, it's called the Harari-Shupe model, which proposes our quarks and leptons aren't truly fundamental, but made out of even smaller parts, preons. These are elementary particles, and they're antiparticles. Mix these two ideas, and you get something pretty unique. Here's the argument. If ordinary matter, what we, see every day, is actually a mix of matter and antimatter bound up tightly together, then its inertial mass, the property that resists acceleration, can be less than its gravitational mass, the thing that creates gravity. That's pretty wild. Okay, let's get concrete. Lush calculates for certain atoms like deuterium, basically heavy hydrogen, that the gravitational mass could be 7 times the inertial mass. Imagine you pick up a block of deuterium and weigh it or push on it. It behaves like it has mass x, but its gravitational pull on other objects, that could be 7 times greater. Suddenly, you don't need hidden dark matter. If every star and bit of gas is weighing more gravitationally than we expect, the observed galaxy rotations make sense. Now, method-wise, Lush takes the preon model and looks at the numbers, literally counting up preons and antipreons in atoms, asking how that composition leads to different mass behaviors under these new ideas. He checks how much extra gravitational pull arises from all this. The paper even refines the model, considers effects like quark-binding gluons, and explores if those account for any dark matter shortfall. Key finding, it's plausible, at least within this framework, that the dark to visible matter ratio matches observations, even if, the explanation is completely different from what mainstream physics assumes. So what does this mean for you, the listener? Well, if you're interested in science, it shows how radically new perspectives, sometimes controversial, sometimes even outlandish, can shake up old questions. It's a reminder that science is a process, a conversation, and that the search for truth is always open-ended. This paper isn't claiming to settle the dark matter debate, and I'm not claiming it does either, but it's a real example of academia's creativity. Let's wrap up. We talked about galactic rotation, alternative relativity, tiny building blocks called preons, and how the way we measure mass could be key to solving cosmic puzzles. No matter the outcome, the heart of research is opening our minds to the possible, trying out new ideas, and challenging what we thought we knew. So, thanks for tuning into In Depth with Academia. I'm Richard Price, presenting this research neutrally as always. I encourage you to read the paper, think for yourself, and keep questioning, because that's what academia is all about. Until next time, stay curious.